Hi and welcome to the lesson that will probably shed some extra light on the complete trigger. And in this lesson we will see maybe the term I already mentioned a few times before, but I didn't want to introduce it, I would say, in a proper way, because it's kind of complex and I didn't want to miss it with mess you up with the concept that was presented in the special lessons in the special lessons. So that's why there is a dedicated topic to watermarks and late data. So that's the question from my previous lesson. How do you know that the state is complete? You don't know it for sure. You can only estimate that it's complete due to some observation, and this observation is the data you are receiving, and or maybe some external hint like external latency store or something like that, but I don't know. I don't think even it exists technically, and most often you will see the watermark implemented as some kind of internal mechanism observing the data is flowing into your job. So the watermark is the definition of how the data that is coming to your job can be. And let's take an example. Here we have some multi-tenant processing. So we have tenant yellow, tenant gray, and tenant orange. And we have some, as you can see, data that is produced irregularly. So there is a orange tenant that is really slow. It's 950 for him. And there is a yellow tenant that is quite fast. It's more real time. It's 10 o'clock, 10:10. Okay. And how in that scenario detect an overall allowed latency? So data is coming. You say that you allow data for the latency of 10 minutes, and you do this algorithm. So you generate the mean event time, so the minimum and the maximum event time, and later you subtract the strategy use, the value for the strategy use from the allowed latency. So as you can already see, for the mean strategy, you allow events up to 940. That's nice, but it applies, of course, has some implication on the state, because if you rely the results emission on the state expiration, of course you will emit these results later. But on the other hand, you have more chance to have complete data in the state. On the other hand, when you choose the max based strategy, you can see that it's the allowed latency is for 10 o'clock, meaning that the orange tenant is already lost. Knowing that this tenant is slow, well, you obviously miss all the data he will sending to you after closing its state. So remember these two implications while you need to choose the watermark strategy, and very often we use the mean one. And how watermark integrates into the processing. So we have before data processing you defined, there is a kind of part under the hood fully managed by the data processing framework you use. Of course, here I'm covering the case where everything is ready. You can try to implement this strategy on your own, but well, it's extra code you will write. And here in the strategy, there is this extra data detection part. So we are receiving data, we generate the current watermark, and whenever we get data that is lower than this watermark, we simply discard it from the pipeline or send it to a separate processing channel for this dedicated to this late data. But that's for what I would say one kind of watermark, yes, right? Because we have it in front, but we can also have another watermark behind. So more exactly in this part. And I would like to introduce two types of watermarks you can find in stateful processing jobs, namely the late data that will filter out all late data in the input, and the garbage collector that will be responsible for emitting the stateful results from the state store to your downstream consumers whenever the watermark expires these records. So whenever the timestamp of these records passes before the current watermark, or whenever watermark passes in front of them. So I already I already presented the late data watermark in the previous slide, and I will just focus here on the garbage collector. So here we are processing state windows of 10 minutes, and the current watermark is of 9:56, and we allow the latency of 10 minutes. And in our state store, we have three open windows that can get data. It's a sample counter, by the way. And for each window, you can see that we have the start and the end time. So now when there is new data coming in, and now with time we will get new data, and of course it will lead at some point to updating the watermark. And here we can say that we reached the point of the watermark of 10:11, which will invalidate this first window, because you can see that the closing time is before the new watermark, meaning that we are not supposed to receive any new data for this window. And of course we will invalidate it and emit these results to the downstream consumers. And you can, with this example, you can already see that the garbage collector watermark is a kind of mechanism to ensure and to have a better control on the state accumulation. So if you don't define any expiration rules for the state, of course you will accumulate it indefinitely. But if you have some time-based rules, as in this case for window processing, you can control the size and the amount of data you need to store to answer the currently processed time range, I would to say. And that's all for this lesson. So remember, there are two watermarks that are concepts to allow control either the input data lateness or to control the state expiration on your state store. Thanks for watching and see you in the next lesson.